What's up, guys? It's Matt from Matt's Math Tutorials. Today, got a pretty short one. This is just a problem from my homework, and I don't think this one should take too long, but it is a little bit complicated to just think about what's happening with this one. So, find the positive values of p for which the series converges. So, um, just for clarity, we've been working on the integral test for finding out if a series converges. So, we're going to use that here. So, the integral test is basically saying if um, we find the integral, if we convert this thing, oh, it's still on the box. If we convert this to an integral, then basically if we find that area, if it's infinite, like if that integral diverges, then the original series diverges, and if it um, converges, then the original series converges. So we're going to convert it to an integral. So, and we want to find the value of p for which it converges. So let's do the integral first, right? So that's going to be integral, so obviously from 2 to infinity, because that's what we're given here. And then we have 1 over x natural log of x to the power of p, and then dx, I suppose. So we want to find the antiderivative of this. So I'm going to separate, because I kind of see two different things happening here. I see the x here, and I see the natural log of x to the power of p here. So I'm going to separate that. I'm going to say integral, right? I'm going to say 1 over x times, and I'm actually going to get this out of the denominator. So I'm going to say the natural log of x to the power of negative p, right? Because if you remember, making this negative means 1 over as a positive, which is what we have right here. But this form I think will be easier to look at. So now, something that should stand out is that you have natural log of x and you have 1 over x. And of course, 1 over x is the derivative of the natural log of x. So really what you have is you have a function here in kind of another function, right? And then you have the derivative of that inner function, which looks a lot like the chain rule, which says that if you have f of g of x, the derivative of that, right, is the derivative of the inner function times the derivative of the outer function with the inner function inside. And so we have something like that here, it seems like, right? So we have this form. Oh wow. We have this form and we want to go back to this form. So clearly we have the derivative. So if g of x, right, the inner function is the natural log of x. Clearly we have the g of x here and the derivative of g of x here. So we have that part covered. But we need f of x, right? So we're going to have a function in a function. And we know that the inner function is natural log of x. So what would turn into negative p when you take the derivative of it? Well, when you take the derivative of a power, what you do is subtract 1 from the power and multiply by that exponent to make it a coefficient, right? So if we had negative p going backwards, we would add 1. And this really would be negative, negative p plus 1, right? Because to fit this, that derivative of f, the f prime, would have to be subtracting 1 from the power, right? So if we had negative p plus 1, subtract 1, we'd get the negative p, but we'd have to make this also a coefficient. So to make this match the form that we want for the f prime, we have to make that a coefficient, the negative p plus 1. But we also, to keep it equivalent as a function, we have to divide by the negative p plus 1 on the outside of the integral. So at this point, now we can replace this whole part with just this, right? And we can double check, take the derivative of this, it would be the 1 over x on the outside times the derivative of this, which would be, right, bring down the exponent, and then times the inner function to the power of negative p plus 1 minus 1, which is negative p. And that's what we have right in here after we add this coefficient out front. So we're good there. So this is our antiderivative. Well, this divided by negative p plus 1. So this is our antiderivative. And so we want this from infinity, or from 2 to infinity. So let's plug that in. Let's plug in the natural log of infinity. I know kind of you're not really allowed to do this, but let's just imagine it for a second, right? Divided by negative p plus 1, and then of course minus the natural log of 2. That one's a little bit more mathematically legal. Divided by negative p plus 1. Okay, so what are we looking for here? We are looking for the values of p for which this whole thing converges. So we want this to basically not equal infinity. Because if this doesn't equal infinity, if we get some finite number for this, or approaches some finite number, right? Then that means that this original sum doesn't diverge, which means that it converges. And that's what we want. We want values of p for which the series converges. So obviously p is going to have some impact on whether it converges or not. So if we want this to not equal infinity, let's look at this in two parts. Let's look at this right-hand part first. Natural log of 2 to the power of negative p plus 1 divided by negative p plus 1. Well, natural log of 2 is just a number. You can find out, the decimal expansion of that pretty easily with a calculator. Now, p is, of course, also just going to be some number, right? Some constant number. So this whole thing is just a constant. So you can think of this as just one number. And if you have, if we had infinity here minus just, like 4.2, it's not going to somehow all of a sudden not equal infinity, right? Similarly, if we had some regular number here on the left, say like 7.1, and then you subtract this, it's not all of a sudden going to be, negative infinity or, some other type of infinity. So basically what we're seeing is, since this is all like basically constants here, it's just calculatable numbers on the right side, it's not going to matter in the grand scheme of things. So what we can do is kind of just get rid of this whole thing, say it doesn't matter for these purposes, right? So we're left with the natural log of infinity to the negative p plus 1 divided by negative p plus 1. So again, we can look at this, I'd say, in two parts, this numerator and the denominator. And I think we could do a similar thing because this denominator is just going to be a number. And if you have, let's say, infinity divided by some random number, right? Divided by k, some constant, you're not going to end up with something that isn't still infinity. You're going to still end up with infinity. And then similarly, if you have something that's not infinity, right, say some constant divided by some other constant, you're not going to get infinity from that. So again, we're seeing that whatever this bottom part is, it doesn't really matter, right? And this, by this top part, it's not, there's no like variable in it other than the p, but it's not like a set value, because infinity like obviously doesn't really exist as a number. So basically, we're seeing that the denominator doesn't matter either, right? It has no real bearing on whether this is going to go to infinity or not. So really, we're just left with the natural log of infinity to the negative p plus 1. So in my head, I'm thinking natural log of infinity. Well, I know the natural log function. Do I know what that does? I think it does something like this, maybe. I don't know. But basically, as you go to the right, it just goes up. And it goes up without bound. It'll eventually hit every number on the y-axis, right? Going up. So basically, natural log infinity, I'm just going to think of like a really, really big number, right? Let's say like this or something, right? This is a huge number, the biggest number I've ever seen in my life. Now this to an exponent, let's call the exponent a, that's just going to that's just going to keep being really big, right? Because I mean, like, this isn't a big, this is like infinity, this is like, it's going to go to infinity, right? Actually, it's probably better to just call this infinity. Infinity to any power is just going to be infinity, right? It's just going to keep going to infinity. But if we have this as a negative a, right, then what we can say is that's actually 1 over infinity to the a, which is going to approach 0. So really, if this exponent is anything positive, it's just going to go to infinity, right? Even if it's like 1/2, the square root of infinity, because natural log of infinity is more or less infinity for this case. So even if it's like 1/2, right? Square root infinity is still infinity, right? It doesn't matter. So as long as negative p plus 1 is above 0, it's going to diverge. It's going to go to infinity. So we want negative p plus 1, this exponent, to be negative. We want this to be less than 0, because then we're going to get something like 1 over, you know, natural log infinity to whatever, right? It doesn't matter. So if we want negative p plus 1 to be less than 0, then obviously we want p plus 1 to be greater, or sorry, I don't know what I'm doing. Add this to both sides. We want p to be greater than 1. So that means that this will converge for any value p greater than 1. And that is our answer. So I don't actually know how long this video ended up being. It looks like about 11 minutes, which is on the shorter side of my videos. Probably my shortest one. I'm actually not sure at all. Um, but I don't think this one's too bad. I think really just knowing kind of what it's asking for and how to apply the integral test, and then once you get the results from that, once you get the antiderivative, knowing what to do with that. Because at this point, you can kind of forget that you're looking for a value of p, right? Because usually finding the antiderivative kind of is the problem. Like that's what you're doing to find the solution. But for this, you do that, and then you have to go another step, which is looking at this antiderivative and saying, how can I make this actually not equal infinity? Um, even though you're kind of plugging in infinity. So hopefully that helped for this problem. Um, maybe some of you didn't actually do the homework already and you actually need help on this problem. If so, this is problem 51, by the way. Maybe I should put that somewhere. I don't know. 51. But yeah, so hopefully this helps somebody. And if it didn't, that's really a modern tragedy. And I am really broken up about it. So I'll see you next week. Math tutorials. Goodbye.